So I'm Martin O'Reilly. I'm a Principal Research Software Engineer at the Alan Turing Institute. We're just across the road at the British Library. We're the National Centre for Data Science, originally set up as a collaboration between 5 universities and the government via EPSRC, but recently announced 4 new partner universities. I'm part of the research engineering team, which is a permanent team of data scientists and software engineers who help our researchers improve the kind of impact of their research by applying it to real-world data science problems, turning research code into sort of software that can be used by researchers outside of the field or non-researchers in business or government. Helping researchers do just enough software engineering to perform so that their work's kind of more reproducible and reusable, and helping researchers make best use of the compute facilities that we've got. We're actually recruiting at the moment, so if you're a data scientist or software developer interested in research, or a researcher who finds themselves writing a lot of software, get in touch. You can be a data scientist, software engineer, or something in between. At the Turing, we're sort of a virtual institute mostly. Most of our researchers are part-time with us and part-time with their partner university, and we've got a small number of postdoctoral fellows working on individual projects, and some fellows who are there on personal fellowships, but most people will have a home university. We've got sort of the same access as other universities to sort of tier 1 sort of Archer facilities, and tier 2 such as Cirrus and the Jade GPU cluster at Oxford. We've got a small sort of Cray cluster, but we've only just got that. So our first year of research operations, which sort of ran last October to this October, Microsoft Azure has been our sort of primary sort of large-scale compute platform, or our only one, and it's likely to be our kind of main platform sort of for the foreseeable future. So our partnership with Microsoft, they've sort of donated sort of $5 million over 5 years, so we get sort of $1 million of Azure per year. So I thought it might be interesting to sort of see how much sort of cloud cluster you could buy with that. So here's some sort of back-of-the-envelope stuff. Big caveat is I haven't factored in storage, and I'll come back to that sort of towards the end of the talk. The first column is sort of on demand, which is your kind of sort of pay-as-you-go, guaranteed kind of availability. The one down the middle is what you'd probably do if you were actually trying to replicate an on-prem cluster in the cloud, which is paying 3 years in advance. And then the one at the end is kind of really interesting, and we're starting to play with it, which is sort of low priority. These are kind of preemptible in sort of Google and Amazon's terms. And to run these, you have to kind of use sort of the batch kind of sort of infrastructure management tools. So they're kind of a bit more of a sort of speed bump for researchers to use, but you get sort of up to 80% discounts, very similar to AWS and Google Compute. When I say HTC, I'm talking sort of high throughput computing. So you want to do, you're sort of embarrassingly parallel, data parallel. You're trying to do lots and lots of the same thing, but each of your compute jobs is kind of largely independent. So you don't need to synchronize your workers or do a lot of high throughput, low latency interconnect. When I talk about HPC, I'm talking about your sort of classical, sort of massively distributed MPI sort of type jobs. I think I mean MPI, I always get MPI and OpenMP mixed up. And then down at the bottom, something a lot of our researchers are keen on is sort of GPU capacity. So we've got sort of the Kepler K80s, the new Pascal sort of P100s and P40s, which sort of became generally available in December. And there's not really much difference in the cost between having InfiniBand sort of interconnect on those. And for comparison, there's sort of like, Archer, a couple of the tier 2 regional compute facilities, and sort of large and medium-sized university facilities for comparison. So if we went and spent all of our $1 million on a cluster of one type, we could probably afford, depending on how we bought it, somewhere between a medium scale university sort of institute facility or a large university or tier 2 facility for high throughput computing. For high performance computing, we're probably more down the kind of medium-sized university kind of institutional facility. And for GPUs, we're probably about half the size of a kind of regional facility. Although the key thing here is we sort of can burst, and at one point we had one of our researchers using something like 820 GPUs for a period of a few weeks. So when we look at how our researchers kind of use Azure, at the moment we've got kind of two sort of major modes. We've got people who want bigger desktops or more of them. So, I want 6 of the biggest machines I can get to kind of, run human parallelized sort of versions of my sort of complicated, high memory requirement code. Or I want high throughput. I tend to be running this on a university cluster, and for this, you talk about hundreds of nodes, or occasionally thousands of nodes. And in both cases, people are very, very keen on GPUs. I think now I'll just talk through a few examples of where we've used Azure to sort of, or our researchers use Azure to do stuff either sort of faster or at a larger scale than they could do with the facilities they had available at their host universities. We've used Azure to sort of support our data study groups, various sort of other projects, and I'm going to talk about the machine translation, quantifying beautiful scenes, and human behavior. The first one's trying to identify where protests are happening from social media photographs, and this is Marva Alaniali, Tobias Priest, and Susie Moat. Here, actually training, it was a GPU deep learning network, but training it wasn't the problem. The scale came in at processing these 25 million images from Flickr. Just getting them down onto the sort of university cluster was a sort of major undertaking. I mean, in the end, they sort of streamed them live from the API, from the Flickr API into the Azure, sort of pseudo cluster that they were using. So processing all these would have taken about 10 months to run on Marva's own computer, and took less than a week on Azure. This was sort of a Dockerized workload, so using Microsoft tool there was Batch Shipyard, but it's sort of a point-and-click orchestration facility, or you can do it on the command line as well. Running, I think, in the region of 300 sort of workers, very data parallel, each of them pulling separately from Flickr. I think, I'm not sure about Flickr, but if you're pulling from something that's well paired, and the files are big, we've seen sort of 30 gigs per second sort of sustained throughput, but anecdotally we find that harder to sustain when we're pulling lots of smaller files. So the second one's Shinuki Ilushka, Suzuki Saracina. This one, the problem was the training. So they needed a bunch of GPUs. So they had scenes, photographs representing 90-something% of the 1 kilometre squared sort of sections of the UK. And they had ratings on how scenic these were on a sort of scale of 1 to 10 from humans. And so they took 200,000 of these images, 1.5 million ratings, and then they sort of trained a deep learning network. And again, sort of you get the sort of speed of months down to days. And then the last one, we've got a machine translation group we work with who can basically eat as much GPU as we can give them. So the results you're seeing here are for a competition in the autumn where they picked 6 languages and did bidirectional translation to and from English in a range of sort of contexts. So in sort of biomedical area or news area, and training a single model for a single pair of languages in a single direction takes about 2 weeks. And parallelizing on Azure meant that they could basically tweak a bunch of hyperparameters of their models, or tweak the structure of their models, and we're able to kind of do this sort of parameter suite that's kind of just not available with the sort of group cluster that they had. This team's actually sort of gone further, and this is the team that was using sort of 816, I think, sort of GPUs over the autumn. So in terms of like what it's been like to have Azure as our only compute resource, the researchers who've sort of grabbed it have kind of really liked it. So I think everyone likes the fact it's on demand and there's no queuing. It's sort of having their own sort of personal sort of high performance or high scale compute facility. And certainly, we've spiked for weeks at a time to usage levels that we just, if we took £5 million, we just couldn't fund the cluster that would spike to that level. Researchers have liked the fact that they can fully define the sort of stack that they're using and reproducibly deploy this to sort of their compute nodes using sort of virtual machine snapshots or Docker containers. And they like the fact that they don't have to sort of queue up or sort of get involved with any sort of IT admin to kind of get their compute running. Although that is also one of their sort of complaints, which is that Azure's got a bit of you can't just lift and shift from either your desktop or a traditional compute cluster. So there's some of the compute abstractions, and especially the data abstractions. It was touched on in one of the talks this morning. They're used to using sort of POSIX, sort of file system abstractions, and switching to object storage, which is sort of the performant cloud storage, requires sort of additional wrappers. And scaling storage is an interesting problem. So for a long time, up till about September, we were telling researchers not to worry about the cost of storage because the cost of compute would swamp it. And that's true up to probably tens of terabytes. Once you start getting to hundreds of terabytes or a petabyte, then it starts to go from being a few cents a month or a few dollars a month to being a few $10,000 or $250,000 a year if you're storing a petabyte. And I think the sort of final challenge we've got is we've gone from being sort of compute constrained to being cost constrained. And if you kind of mess up your forecasting for a fixed sort of compute capacity, you sort of just wait it out and you can sort of not quite start again, but you've got the rest of the year to balance things out over. If you sort of burn up all of your compute resource in the first sort of 6 months of the year, then you've got a bunch of researchers who can't do what they need to do. On the other hand, if you ration it too much, then you end up not getting the best use out of it, because at the end of the year, you've got this big surplus, and the only people who can use it are the small number of people who can do hundreds or thousands of nodes in at short notice, which is few and far between. So that's sort of part of what our team's sort of there for, and the types of things we've been doing to support our researchers are some training sessions. We run these on a kind of annual cycle at the moment. Then throughout the year, we've got Azure Club drop-in sessions. We've got sort of come and talk to us and we'll help you out support. And we're trying to sort of develop some, and Beg, Borrow, Steal, tie together some orchestration scripts and best practice for making the sort of using these sort of batch kind of management things, make these easier. And our goal is to kind of end up with it being as easy to use as yours to use your kind of desktop computer, or maybe that's a bit extreme, maybe your local cluster. Yeah, that's that.